Hello. Okay, so I'm going to go over this worksheet, but I'm not going to go over all the answers because um, I need to give you guys some incentive to come to S2I. And I know it's really challenging with it being on Zoom, but if you haven't already, please fill out the survey about scheduling because the Monday time can definitely change if more people are going to come at a different time. Because this is the first one, please email me any questions over the ones I don't go over. You can actually even text me if you want. I don't know if I'm going to do this for every worksheet if nobody comes to S2I, but here's if you want to take a picture of what you do have and send it to me. That's my number. So I'm not going to go over naming or anything on the first page. I'm going to let you guys do that. If you want to check your names, what I like to do is I like to go onto Marvin Sketch and I like to draw out the structure, and then you can click, if you highlight the entire structure, you can, I think it's, what is it? Structure tab, and then it will go down and then it says generate name. You can click that, but that gives you like two names and there's a bunch of names for everything. So then there's that. You could have named it correctly, but didn't list. Okay, so I'm going to go over some of the reactions. These are some old ones that I just want to refresh you with. So first one, ozanolysis. You're going to break this bond right here. And there's 6 carbons, so I'm going to draw 6. 1, 2, 3, that was 4. 1, 2, 3, 4, 5, 6. And then double bond O off each of those. Second one, you need an oxidizer. So like this is an oxidizer, bleach, chromate. If you can think of any others, list them. So this one is, I was kind of lying when I said prepare alones because that's makes a carboxylic acid. Oops. That is not an oxygen. Okay. So, oops, there we go. Alright, so if we keep moving down, this one doesn't have an H to grab off of this carbon, so it's going to be no reaction. And PCC is a special one where it takes primary alcohols and transitions them into aldehydes. So that's preparing ketones and aldehydes. Now, this one is, whoa, what just happened? Oh, sometimes my computer is weird and does. There we go. Okay. Don't mind me. Okay, so this one. Now we're comparing which one's more reactive, the aldehyde or the ketone. And in class, if you guys were there, remember, aldehydes are more reactive because of they have less steric hindrance, and then they also don't have these carbons to kind of stabilize the partial positive charge. So for lithium aluminum hydride, it's going to react with everything, so everything's going to become an alcohol. But for this one, only the aldehyde. Alright, moving on. So I kind of wrote this question poorly based on the arrows. So it's not no reaction, but it's just going to favor the reactants, if that makes sense. So the arrows would look more like that. So for the first one, it's going to be, there's going to be an O with negative charge because that's going to attack there, bring it up. And then there's also going to be an OH. And how many? 5. And then for a second one, it's going to be kind of the same thing, but with ether group. Not that great at writing on the screen yet, so be patient. And then for the last one, remember when acid, the ketone, that oxygen is gonna grab that proton first. So it's gonna be OH, OH. That. And then for the next one, I hope you guys know this one, Grignard. It's basically an ethane with negative charge. It's going to attack that. And then next step, when you add water, it's going to pick up a proton. So it's going to look like that. 1, 2. And those ones are kind of confusing, so remember always label if it's like if it's bigger than ethane, then you'll definitely want to label your carbons. And so I'm not going to draw the mechanism, but I am going to draw the hemiacetal and then talk about that for a little bit. So, 1, 2. Oh. So I'm just going to draw, it was pH with the phenyl group. That's going to be OH. Oh, I drew that wrong already. Oh, no, I didn't. Never mind. Okay. And then O, and then 1, 2, 3. 1, 2, 3 carbons. So here's the hemiacetal. And what's going to end up happening is the hydroxy group is going to pick up a proton and become water. And this is an extremely good leaving group, so that's going to leave. And then the reason why it's so good at leaving, not only because it's a great leaving group, but also because this carbocation that's formed has resonance with with the oxygen. It's a little messy, I know, sorry. One, 2, 3. Okay. So there's that. Alright, so question number 8. I'm going to do the first one and then have you guys do the second one. If you want to text me again the picture of it, I can double check. Otherwise, after the first one, you guys should get the hang of it. So, the hemiacetal is going to have a hydroxy group with an ester, and the stereochemistry is going to stay the same. This one right here is racemic, so it's both. So it's a chiral center, and both of them are going to form, but these are going to stay the same. And then when it becomes an acetal, so I'll write that. When it becomes an acetal, that chiral center is no longer chiral because both of these are the same. So it's going to look like that. So you guys can do this one if you want. And then for synthesis, I'm also not going to give you the synthesis answers. I want you guys to try and come up with a synthesis pathway. And review some old stuff, because this one has some older stuff. It's not, I shouldn't say too challenging because I made it. But I hope to see more of you guys at the Monday session. But if you guys can't make it to the Monday session, I'm probably going to do another video like this and send out another survey seeing a better time for people to come. So that'll be it. Thank you guys. See you in lecture, kind of.